I'm going to do something a bit different today. Instead of trying to solve problems as fast as possible, I'm going to try and do more of a tutorial. So I'm going to go slower, try to talk a lot more about what I'm doing and thinking. So hopefully that's interesting and useful. This is a Codeforces Div3 contest, so it's the easiest contest, level of contest that they have. So hopefully the problems aren't too bad today. Yeah, so let's give it a try. Jump right in. Okay, so I typically go through the problems in order of difficulty. In Codeforces, you can see how many people solved it in the actual contest, but usually they're in order by difficulty. So let's see what this is. Okay, the new year is coming. We have the 24-hour clock format, H&M. How many minutes before the new year? The new year is 0 hours and 0 minutes, and there are T test cases. Okay, so now I just want to scan through the input and see if that makes sense to me. So there's 5 test cases, and this one is 11:55, so it's going to be 5 minutes. This one is 23:0, so it's going to be 60 minutes. Okay, so this is making sense. T independent test cases. First line has test cases. I don't know why it's 1439, but whatever. They guarantee that the time is not midnight and that there are no leading zeros, and we should just print out how many minutes before New Year. Okay, so this seems straightforward enough. For each test case, read hours and minutes, and then the answer is going to be 60 minus the number of minutes, right? Because you need to roll over to the next hour. And then, what is it? 23 minus hours times 60? Because you're going to get 1 extra hour from rolling over the number of minutes. And then you need to make up the rest, however many more hours there are until 24. That's why it's 23 minus instead of 24 minus, and there's 60 minutes in an hour. Okay, so that seems fine. I'm going to do it in C++. So the first thing I always write is include IOStream. That gives us our input-output functions in C++. Include is like import for C++. And that's actually all we need for this problem. I'm using namespace stud. So a lot of, basically everything in the standard library is supposed to be like prefixed with stud. But I don't know, it's kind of annoying to type that all the time, so this just says that you don't need to put the namespace in front of everything. And I also like this abbreviation. So this is a type def in C++. So this is an abbreviation for this, and this is 64-bit integers. I could also write, maybe this would be a little more correct. Long can vary depending on exactly what computer you have, although typically it's 64-bit. Anyway, so we're going to have a number of test cases, and then we can read that in. And then we're going to loop over that number of test cases. And we have hours and minutes. Hours and minutes we can read in. And then we said the answer is 60 minus minutes plus 23 minus hours times 60. And we can see out that answer. So that's pretty much what I talked about, right? That we need to roll over to exactly the next hour, 60 minus minutes. Even if minutes is 0, we can still do this, and that'll just, we'll get the full hour then. We could also special case mx 0, but it's nicer not to. And then because we've already gotten an hour from the minutes, we only need to get up to 23 hours. So 23 minus how many hours we have times 60. And then we just print out the answer. So that should be the problem. So now we can test our code. So I'm just copying the input. I'll open up. So I've saved that input to a.0. I like to just name my test cases, right? So I like to name my solution a.pi.a.cc, the name of the problem, and then my inputs a.0, and if there's more test cases, maybe a.1, a.2. So in this case, a.0 will be fine. So let me g++ a.cc. Right, this compiles my code, and now I have a.out. And so it's nice to be able to run and compile the code in the same command, so that's what this is doing. And then I run my code, and I redirect standard input to a.0. right, you'll notice that my code never mentions any file about a.0. It just reads in from standard input. So, you know, this is, I could also run it sort of interactively, right? So this just tells it to, instead of taking input interactively, take it from this file. Anyway, so I got the outputs 5, 60, 1439, 1180, and 1, and 5, 60, 1439, 1180, and 1. 1439 seems to be a significant number, not quite sure why. Okay, so let's submit this code. So problem A, language C++, source code, I'm going to choose a file. There's my file. Submit, and now we can watch it being judged. Right, it's running right now. In a contest, I might go and start another problem, but I think I'll just watch it. Okay, so we got accepted, so that means it's correct. Cool, so that was problem 1, not too bad. Right, now we can see that we finished A, so let's move on to B. Candies division. So we have N, Santa has N candies and wants to give them to K kids. You should divide them as equally as possible. And you can't divide the candies in parts, but you are allowed to not use any. Minimum candies is A, maximum candies is B, so they need to be off by at most 1. And number of kids who have A plus 1 candies is not more than half. Okay. Well, so certainly we can do integer division of n by k. This gives us however many candies we could give to all the kids, so we definitely want to do that. And then we can hand out some extra candy to, at most, half rounded down of the kids. So we can hand out, you know, k over 2, the min of k over 2, and however many candies we have left. So that seems to be the answer. And the input format is very similar to the last problem. First number of test cases, and then each test case has n and k. And we should print out the maximum number of candies that we can give out. So I'm just going to copy the code for the previous problem for this problem. And it's similar. We have the same test case set of code can be reused, the same, you know, IO, stream, std, ll is all fine. A. Okay, so problem is using A for the minimum, so I will do the same. The remainder is just n minus A times k. And so we can give out the maximum of how many candies they have remaining, and k over 2. And that should be the answer. And we may need to include some header file to get std_min. I guess we'll find out. Maybe not. Okay, I should actually copy the input into b.0. So again, the sample input. So we got 5, 18, 10, 6, 7, 5, 0, 1, 5. So that looks good. Okay, let's see if this is correct. b.cc, submit, running. Cool, so that one's also correct. Yeah, so it was pretty much what I said. We figure out how many candies you can hand to everyone, and then we can hand out the rest, the minimum of how many candies you have left, and half the kids. Okay, so problem 3. So n friends want to give gifts for the new year. Give one, receive one. Can't give to yourself. It's a secret Santa situation. Either he knows who he wants to give the gift to, or either he doesn't know who he wants to give a gift to, or he does know. So fill in the unknown values such that everyone gives and receives exactly one gift, and no one gives a gift to himself. So there's at most 200,000 friends. Very big friend group. All these stories are like very reasonable, and then they're like, yeah, there's 1 billion floors, or there's 200,000 people in this Secret Santa group. Anyway, and then we have n integers, which are who people want to give friends to, who people want to give gifts to, and also 0 if they don't know yet. And we should fill in the zeros. I guess that's supposed to be new f of I. Looks like multiplication. Yeah, so all the values must be distinct, and they can't equal themselves. And that's actually the only restriction, right, if you think about it. Because if all the values are distinct, that means that everyone receives one gift. Just the sort of the output format means that everyone gives one gift, right? Everyone's only, this is who you give your one gift to. And NFI can't equal to I is just the condition that you don't give a gift to yourself. So this sentence is actually redundant with this sentence, this is a nicer sort of way of seeing it. Okay. There's several answers. You can print any, fine. Yeah, so we just need to fill in the zeros with what? With something that meets these conditions. So how exactly are we going to do this? So let's figure out what values are missing from our list. So we'll use a set to do that. Right, so this will start with the set 1 through 5, and then we'll take out 5, 2, and 4, leaving us with 1 and 3. And in this case, 3 shouldn't give a gift to himself, so he has to give a gift to 1, and then 2 can give the gift to 3. So what is the general way to satisfy, like this, satisfying this is trivial. What about this? This is like super obvious. Well, I mean, it should be not that hard because there's only one person that you can't give a gift to. Even like a random assignment would do it most of the time, I think. We can maybe start by assigning everyone themselves and then just rotate by 1. Let's give that a try. So again, we'll start with the same set of code. I think now we're going to want to use vector, which is like a list, an array. So this is only one test case. So we're going to declare a vector of 64-bit integers of length n, starting, they're all 0, and then we just read them in. There's a sort of one indexing problem here, which is these values, right, in the problem. These are one indexed, right? This goes up to 5 instead of 0 through 4. So I'm just going to treat them as 0 indexed, and I make sure to put them as one indexed later. And D are the values that I guess I'll fill in. So what's my idea? Right, so there's two things that I need to fill in, right? There's a bunch of people who are zeros. And there's also a bunch of, so there's a bunch of people who haven't given gifts and a bunch of people who haven't received gifts, and you have to pair them up. So let's just make a list of both of those things. So I is going to be people who haven't given gifts, that is their AI equals 0. And UI is false if UI hasn't gotten a gift. So yeah. So we're gonna pair them. How are we going to pair them? So if this guy hasn't gotten a gift, okay, so the idea that's one reason why I find it hard to talk through these problems, is that I didn't have a clear idea before I started coding this how to do the problem, which I kind of knew, but I thought I would get a better idea by sort of working on it, working through the code rather than thinking about it more. So I sort of jumped in without a clear idea of what I'm going to do, but now I think I'm getting there. So I'm going to keep track of who has gotten a gift, who has sent a gift, and then everyone, if all the people who both haven't gotten and haven't sent a gift, I'm going to make a cycle with those people. So I'm going to start up pairing them with themselves, and then I'm going to rotate them by 1. Right, so like if 0, 1, 4, 5 haven't gotten and haven't sent, then I'm going to have 0 send to 1, send to 4, send to 5, send to 0. And everyone else who hasn't gotten or sent can pair up arbitrarily. So it's going to be this vector of both. Every time AI is more than 0, that person sent a gift and the recipient got the gift. And remember the sort of one indexing that we talked about. So now we can go through and populate the both vector. Now we can go through and implement. So now I've made the list of people who haven't gotten an event sent. Now I'm going to implement this idea. So A of both I equals A of both of I plus 1 mod both that size. last person to send to the first person, so hence the mod. And it should look like that. Okay, and okay, now both sent and got a gift, and now I can just pair up the remaining people, as I said, arbitrarily. So I guess the simplest way to do that will to make a list of them. If not dot I. If not sent I, not sent back pushback I, and now I can just have them send gifts. And there's an assertion to write here, which is that it should be true that the number of people who haven't gotten a gift is the same as the number of people who haven't sent a gift. And so I'm actually going to write down that assertion, because whenever there's something that should be true, it's nice to just check that it is true, so that you'll see it if somehow your logic is wrong. So a of not sent I equals not got I. Okay, and now we just need to print out the answer. So if we're not at the end of the list, then print out a space afterwards, otherwise print out a new line. And okay, I think that's it. So let's test out our code on the input. So we have lots of inputs to try. And I've actually realized that there is a problem with this code. Several problems, in fact. So one is that this one indexing needs to happen. So we'll just, whenever we write something in AI, we solve that. But a bigger problem is that this idea that I had is not right, because suppose that only one person has not gotten and has not sent a gift. Then they're going to send to themselves, according to this strategy. So that's not good. Okay, so what do we do if both dot size equals 1? So then we're just going to special case this, I guess, at the beginning of this loop. So sort of a mess, isn't it? Is there a nice way to handle this? I mean, it would have been better. Well, okay, it's fine. So we must have at least 2 people who haven't gotten presents. So if the first guy is not equal to the both guy, then we can send to him. right, and then delete the guy who got the gift, right, from the people who need gifts, and both 0 from the guy who sent the gift. And otherwise, we know that we can just do the same thing with not got 1. Yeah, so that's ugly, but it should work. Right, so the idea here is if there's exactly one guy who hasn't sent and hasn't gotten a gift, then as I mentioned, my strategy is messed up. Right, he just sends to himself. So instead, I'm only going to do that cycle thing if there's more than one guy, who both hasn't sent and hasn't got a gift. And otherwise, I'm just going to do this kind of brute forcey thing where there must be at least 2 people who haven't gotten and sent gifts in that case, otherwise he would have to send to himself. So send to, if he's not the first one, then have him send a gift to the first one, and if he's not the second one, then, then if he's not the first one, then he must be able to send, if he is the first one, then he must be able to send a gift to the second one. And then, I can update these lists. These erase calls are slow, they're O of n, but I'm only making 2 of them, so it's fine. And then I can, still go and assign everyone arbitrarily after that. That should be correct now. It doesn't compile. How does erase work? Let's see, it takes an iterator. What a mess. Okay. So we're actually always sending something from both, so we can just do that in both cases. Right, so we can use begin plus however many we want to erase, in this case 0, and 1. Oops. Okay, 5, 3, 1, 2, 4 was the correct answer. Right, so the bug I just fixed is that I was trying to erase both 0 from not sent, which doesn't make any sense. You should erase something in not sent from not sent. So I need to find both 0 and not sent and then erase that. So this whole thing is a huge mess, but I believe it's correct now. So let's see. Seven. What was C.0? It's probably easier just to think about whether or not our answer can work. So indeed, 7, 1, 4, 6 is fixed. 2 is sending to 3. 3 is sending to 2. That was the cycle. And then 6 is sending to 5. Beautiful. Okay. So here's another one. Okay, so we have 3 is sending to 2, and 5 is sending to 6, which seems fine. And here we have that 3, 4, and 5 weren't sending gifts or receiving gifts, so we have, this is now the cycle, 3 send to 4, 4 send to 5, 5 didn't send to 3. Cool, so that seems to be correct, so let's give it a shot. Yeah, the code for this seems really gross. I don't know if there's like a nicer way to do this or what. I don't know, it's kind of a weird problem where, you know, pretty much it's not very hard to find a solution. And indeed, I'm still probably like a simpler solution would have just been a randomized one, which is just among the people who haven't sent and received gifts, just randomly pair them up, and then check if there's any violations of the don't send a gift to yourself condition. And you'll probably find one pretty quickly. I think the number, right, this is related to the number of derangements, because a derangement is a permutation where no one points to himself, right? A gift giving is just a permutation, and a gift giving where you don't send a gift to yourself is just a derangement. So sort of the fractions, the number of permutations that are derangements is 1 over e. In our case, it's even sort of better than that, because the number of sort of people who still need to give gifts and receive gifts, they may not be the same people. So then it's easier to avoid giving a gift to yourself. So if we just do a couple random assignments about e of them, which is like 3, then we'll probably get something that works. So that would have been maybe a simpler solution. It's a randomized idea. But, you know, we found at least I hope we found a deterministic solution. Just a bit uglier. And still running. 139 test cases. That's a lot. I guess that makes sense that there would be a lot. Okay, so that was correct. So yeah, interesting problem. Let's move on to problem D. So there are n Christmas trees on an infinite line, and they grow at distinct positions. So every point can be occupied by a Christmas tree by the human. Okay, I guess there's going to be a human here, or not occupied. And only integers matter. Oh, the human or a human? Okay, well, we have people who want to celebrate Christmas that are also on the line. And they, yeah, okay, so it should be a Christmas tree, a human. Anyway, distinct integer positions, and we want to pair up the people and the Christmas trees. No. I see. We need to pick positions for the people such that they're all pretty close to the Christmas trees. Okay. It's a weird problem. Okay, so we have a bunch of Christmas trees, and we need to assign positions to the people, and they should be as close to the Christmas trees as possible. Sure. So I guess the point is, right, sort of naively, you would just want to like put 2 people on each side of a Christmas tree, or maybe if there's only like 1 Christmas tree and you need to place 100,000 people, you know, they just sort of stack up really close to it, which is going to be basically the answer, but the Christmas trees might sort of be blocking, right? If you have a bunch of Christmas trees next to each other, then the people can't stand on them. So again, like the last problem, it feels like this is not sort of that, it's not going to be that hard, but it is maybe kind of going to be a little bit painful. Yeah, so the positions are all up to 1 billion, and my positions can be up to 2 billion, which should be plenty. And, you know, none of the people can overlap with themselves or their Christmas trees. So, yeah. Again, this is a problem where it feels to me like it's going to be easier to think about once I actually sort of start coding it instead of just abstractly looking at the problem statement. So I'm going to do that even though I don't have a sort of full plan yet. Okay, so we had n and m, and n was the number of Christmas trees and m was the number of people. I'll call it x like it was in the problem statement. Okay, give me. No, be right back. Okay, I am back. Okay, well, so here's one idea that I think is not going to work out, but it sort of makes some sense to me. Consider positions in order of distance, left, right, which tree, right? So we have like x 0 minus 1, x0 plus 1, x1 minus 1, x1 plus 1. So, you know, if these are sort of obviously optimal because we're going in order of distance, and then, you know, which tree that we're centered around and left, right is fine. So the problem is that if enough of these positions are occupied, this might take a long time. So imagine that we have all of the trees clumped up, which I think might be the worst case. Then, yeah, it's going to take us like roughly m over 2 iterations, which is, you know, 10 to the 5 to find positions for all the people, because they need to, you know, obviously the solution in this case is that they need to stand on opposite sides of the clump. Right, so that might take m over 2 iterations, and each iteration is like n times, so that's actually 10 to the 10, so this is a bit too slow. So the next thing that comes to mind is, what if we merge clumps? So that, you know, 2 adjacent trees we don't try to expand out. You know, if we have trees A and B, we only try to expand left from A and right from B. If we have A, B, C, we don't try to expand from B at all. So what if we just have like dots in the middle? Maybe we need to sort of dynamically merge these. Yeah, okay, so let's try that. So I'm going to keep iterating over clumps. So there's going to be, this is which clump pi is part of. Right, and then you tackle these sort of left and right vectors, which is the left and rightmost tree of a given clump. Is this going to work? So what if we do actually have a bunch of individual trees separated by dots, and I don't say that they're each their own clump? Is that going to be a problem? Yeah, it is still a problem. So we should try and dynamically merge these clumps. So basically, whenever you add a new person, you check if there are trees to their left and their right. And if there are, then you merge those two clumps into a bigger clump. So this is going to be actually like a union find idea. So let's look at that algorithm. Just trying to set find. So the idea is that we have these individual sets or trees in our case, and we want to be able to merge two of them together. It's actually a very simple algorithm. So there's two functions. There's find and union. So find tells you, given a tree, which clump is it in, and union tells you how to merge two clumps together. So I'll just code it up. So if clump x is equal to x, so if x is the identifier for a clump. So the idea here is that we have well, let me write it down first, and then I'll try and explain it. So this is a pointer to, okay, so let's think of it as like this hierarchical structure where every tree is going to have a manager. That's maybe the right way to think about it. So all these clumps have little org charts, and if a tree is its own manager, then it is the leader of its clump. And to find the leader, to find your leader, right, if you're a given tree, you sort of just walk up the org chart here until you find, the guy who's his own manager. So if you are your own manager, return yourself. Otherwise, find out who your manager's manager is and return him. And now this is an optimization called path compression, which says that you should just reset your manager to whoever sort of the ultimate boss of your clump is. And the idea is that this means that we only need to traverse a given path once. So if we have some very long org chart, right, sequence of bosses, and we keep repeatedly querying the guy at the bottom, that might be quite slow, right? He has to walk the whole thing every time. But we know that he's always going to get the same answer. So if we just write down that answer, then things might be much faster. And actually, it turns out that this improves the entire performance of the algorithm from n squared to n log n, which is a big improvement. So the other function I'll call merge, which takes takes two trees and merges their clumps. So first we need to find the managers of both clumps, and then we just say that the manager of one of the clumps is actually, right, so we say that now px's clump is going to be managed by py. And so this is how you get sort of non-trivial log charts here. Okay, and actually, I guess in this case we have some special information that we want to keep track of, just left and right. So I'm just making these things global variables so I can manipulate them by these functions. And so the left of py is the min of the left of px and the left of py. Right, my new leftmost tree is the and the right of py is the max of the right of px and the right of py. Right, so my left and rightmost trees are just the best left and the best right from both of my constituent clumps. So initially, we can say that every tree is its own clump, and it itself is its right and leftmost tree. So now we read in the input, and now we can go through. Are these sorted? Let's just sort them. I believe sort is in the algorithm header. And we'll have it be the position rather than the index for left and right. And now we should merge together adjacent clumps. So and we don't want to overflow, right, I plus 1. So yeah, now we merge together adjacent trees, and okay, so well, we need to place more people. So we'll just, yeah, we'll go through different loop distances. So one tricky thing is here is how do we actually iterate over the clumps, because we're using arbitrary trees to represent them. So we're just going to keep track of which things are the roots, and then we can erase. Right, so PX is no longer the manager of his own clumps, so we just erase him. So left of clump minus D, or so we'll also keep track of a set of used positions. So we should, I guess, insert this. We need a mapping from positions to their clumps. Right, so what we want to say is so let's say if I was going left and there is a clump to my left. There is one and clump dot count plus +1 merge Yes, this is actually going to be a map from position. So that means we need to map, that's fine. And I guess we are using a bunch of sets, so let's include set. And there's some issue with iterating through sets while you're modifying them, and this might modify root, so let's just iterate through a copy. I think this should be fine. And we can keep track of the actual answer. verbose go to. Right, and so we should just output let's see, we also need to keep track of the total distance, so that's fine. Call that lowercase answer. And we have that chance plus equals d, so giving over distances. And we could output the array, same code as last time. Compiles, that's possibly a good sign. Segmentation fault. Okay. What the segmentation fault is, and it's that I did not declare left and right. That's fair enough. Okay. Right, so what was happening with GDB? So I ran it. Some special sort of syntax that you need to run it with. So you need to compile with the -g flag, which tells it to includes debug information in the executable, and then GDB my executable, and then I can, all I believe is to run with an input file, and it runs it, and in this case prints out the answer, but it could also crash, and if it crashed, we would get a little bit more information, as we did. Okay, so we're claiming the answer is 8, which is good. That's what they think the answer is 2. And the trees were at 1 and 5, so you can 1 and 5. So how are we putting a person in 5? That doesn't make any sense. Instead of you, we actually just want to use clump. That's what we said. Some debugging output. What is this U thing? A little bit of that. We don't want to run it anymore. Let's run it on the command line. Oops. Okay, so there were trees at 1 and 5, so we initially go left at 1 and 4, and then right at 2 and 6, and then left again at -1 and 3, and the answer is 8. That seems extremely reasonable. How about this one? So we got 13, they got 7, so that's not good. No, that should be okay, actually. Okay, 2, -1, looks fine, -2. Wait, so what did they... Okay, that's why we have the debugging output. And just to remind ourselves, the input is 0, 3, and 1. So we have one clump, which is tree 0 and tree 1. No, one clump at tree 3. Fine, I guess. Yeah, that makes sense. Right, so 2 goes from there, -1 goes from there. Let me find out all the positions that we're considering. Something seems to have gone wrong with that. It should be y. I had x, so I was merging the thing with itself, so that's not good. Okay, now I get 7, which is correct. And indeed I get -1, 2, 4, -2, 5, which is the same thing they got in the reverse order. Okay. Technically C-error. C-error means print to standard error, which is different than standard out. Although in the terminal it just goes to the same place. So anyway, that's maybe a nice way to distinguish debugging output. At least you can search through your code for C-error instead of C-out. Okay, so let's see if this is correct. So I'm actually less confident in this one. You can see the problems are getting harder, which is, I suppose a good sign. But yeah, we basically followed this strategy that I was talking about, but it did sort of require refinement, doing the coding as expected. It was not all planned out ahead of time. So we had this map from positions to which clump they were part of, the left and the rightmost trees for each clump, and then the set of clumps. So this was this is the union find or disjoint set algorithm. So we have the find operation, which just walked up what I was calling the org chart for the clump to find the guy at the top, and then short circuit that, look up, that's path compression, returns him, and then the merge or union of two clumps, which took two people sort of anywhere in the org charts, found the boss of each clump, and then said the boss of px is now py, so the whole clump sort of goes under py, and so the the new left for the clump is the min of the two lefts, and the new right is the max of the two rights, and now px is no longer a root. Okay, so we read in the number of trees, the number of people, we read in the positions of the trees, we sorted the trees, kept track of left and rights, and now we sort of formed all the clumps. So initially each tree is its own clump, and it has a presence at its position, and the left and the rightmost trees of each clump is just the tree itself, and each tree is a root. And then we went ahead and merged adjacent trees into their own clumps. Notice, if there's so many trees in a row, this will form one big clump because the ith clump will already be big. Right, just sort of, the clump on the left will be as big as it needs to be. So we will actually form big clumps this way, even though we're only merging together two adjacent trees at a time, because the leftmost tree might represent sort of a large number of trees to its left. And then we just iterate over the positions in sort of the order of the naive thing that I was talking about initially. It's still too slow. Okay. In the order of the naive thing that I was talking about initially, and right, so if we're already done, then stop. Make a copy. This part might be too slow, so make a copy of the trees, or the clumps to iterate through the clumps. Check the positions. Yeah, okay, I'm kind of surprised this is too slow. So if that position is empty, then add a new person there, and potentially merge with a clump to our left or our right. Okay, so what's slow? Obviously this part. So 200,000. Let's just check this and see if that's fast. It seems tolerable. Half a second. Okay. We just make a generator for this, because we're going to want to try some big cases. So I'm writing a program to generate test case files, bigger test case files. That's, obviously we don't want to type in 200,000 numbers by hand. And I forgot about namespace third and defining LL. Okay, now we can run. Let's give it a name. Oh, whatever. It's going to go to Div3. Took 3 seconds. It's supposed to take 2 seconds. Okay, so maybe it's just that's the problem. What happens if we do this? Yeah, but if we only make it 100,000 feet so that the people have to spread out at the end, does that make it worse? So I have a little bit less output. Seems like we're not placing people very fast. Constantly iterating it. For the first iteration, it should be a very small number, I would think. Yeah, okay, so that doesn't seem to be working properly. So let's just look at a couple. Just the first few iterations. Something's going on. Well, how about d equals 1? D equals 0 doesn't seem very useful. itself. I'm trying to turn anything from here, trying to. Yeah. Maybe I can sense this. Yes, okay. Let's see. Space position. Okay, yeah, there's some ambiguity here about whether clump contains positions or indices. And it's meant to contain positions, so let's just be more clear about that. means you should only call find and merge on positions. Pointing to I, but all B is pointing to yeah, okay. I needs to go through positions. Return true if it actually did a merge. Okay. Still kind of sketchy on the time limit, but I don't know, might be okay. Yeah, so what even happened there? So we had this bug about whether or not we were thinking about positions or indexes in these maps. And I switched to indexes, which is slower because now we need to traverse these maps all the time. But you know, it's correct. So now it's doing what we want. And then we were recomputing these. So the question of like what clumps to iterate through continue to be a problem. Because if we recompute it every time, it's quite slow, right? If there's only one thing to go through, but we're recomputing it, that's like O of n time every time through the loop. So only on a successful merge am I recomputing it. And that turned out to be fine, right? We've now been accepted, and we ran in 1.5 seconds, which was under 2 seconds, but not by too much. So yeah, mean find. And that was kind of a messy implementation. You know, I didn't quite know what I was going to do going into it. Changed my mind a little bit. You know, had this sort of type ambiguity about whether or not we were dealing with indexes or positions in these maps. Unordered map might be faster than map. That's a hash table instead of a BBST, instead of a tree set. Oh, okay. It's problem D. Let's look at problem E. How long have I even going? I don't remember. Anyway. Okay. New Year parties. Hey, it's the New Year. How convenient. N friends live in the city on the number line. They live at XI. You can only move at most one square. And you can go sort of off the line. I see. So everyone moves left or right 1. And what is the min or max number of distinct numbers that we can have in that case? Okay. And there's 200,000 friends, and they can, you know, occupy up to 200,000 positions. Seems not so bad. Right, just move left, go through each person from left to right, move left if the left square is empty, stay put if your square is empty or has not been occupied yet, and then go to the right if your square has, if that square is not, or otherwise, I guess. I see. So that's how to get the maximum number of possible occupied houses. How about the minimum number of possible occupied houses? So I think it's the same thing, just in reverse. That is, well, if you can go to an occupied square, do it. Otherwise, go right, which will help anyone after you go to an occupied square. Okay, this problem actually seems easier to me than the last one, so maybe I'm just missing something. I guess we'll see. Okay, so we can delete a bunch of this junk. And and we can do max first, I guess. So whatever. Just count it up at the end. Okay, so that was maximizing. For minimizing, we said if there was a place to go that was already occupied, then do nothing. Else, min, let's go right. And then just count the number of occupied houses in each case. Right? Two and 4, good. Three and 8, good. Three and 6. Maybe this is easy, and it's, I mean, it required some more. You have to have some confidence in this greedy solution, I guess. It's not obvious that it's correct. Okay, so that worked. So this, for me, this was much easier than column D. So how does the greedy solution work again? So the fact that they're sorted is very key. So because they're sorted, you know, if you want your neighbors to end up in the same house in you, if you don't want them to end up in the same house in you should try and move left. And if you do want them to end up at the same house, you should try and move right, because all the people who are going to make their decisions after you, are all to the right of you. So that's very important. So if we want to maximize, then if there's no one, if the left house is empty, then we should go left. And this just makes it easier for everyone after us to have new places to go into. So we should go basically to the leftmost place that doesn't have anyone in it. So if there's no one to the left, go left. If there's no one in the, where we are, stay where we are. And if there's no one to our right, if there's someone to our left and someone where we are, then we might as well go right. And to minimize the number of occupied spaces, well, if you can go somewhere that's already occupied, great, do that. That does nothing. And otherwise, always go to the right. So that the people after you, have the best chance to sort of huddle up with you. So this is a sort of a purely greedy solution. Once you sort of get the idea for it, it's very easy to code up, but you have to have the idea. And again, the sorting is very important because we're really heavily using in the solution the fact that all the people who are going to make decisions after us are to the right of us. Okay. So that was column E. Yeah, not too much to say sort of code-wise there. Right, we're just going to have these vectors of occupied positions. They can be of max size so that there's no, no issues with out of bounds. And they can be vectors because 200,000 is not so big. Right? If the positions were like up to 1 billion or something, you probably have to use sets, but they're smaller, so it's nice to use vectors. Okay, problem F. This might be hard. Only 150 people have solved it. Might be too hard for me. Okay, so we want to install a garland. And it's going to be a tree. Whenever there is n vertices and n-1 edges, that means you have a tree. So one lamp is the root of the tree. Yes, and we're going to do wires. The wires connect to lamps, yes. And the parent and the child, right? So it's good to translate all these story or flavor terms into sort of, you know, more mathy terms. So the parent and the child, yes, every lamp has one parent. Every lamp has a brightness value, okay. The importance of the wire, I see. So we have the tree. Oh, interesting. I see. So we have the root of each edge in order of importance, and we want to find out the child of, no, we want to get the full tree, basically. Okay. Interesting. So what's going on here? Okay, so we have the parents of each edge, but we don't have the children, and the only other information we have is that is some weird thing about the order, which is that they're ordered by the sum of the weights of the vertices that you would have to disconnect, or that you would disconnect by cutting this edge, which is a very weird condition, but let's think about it. So it must be the case that the first vertex mentioned is always the root. Because the most important edge must be down from the root, right? Any edge that wasn't from the root, well, you know, take its parent edge, right? There's some edge from the root that contains that subtree. That would be more important. Okay, so that gives us the root, but what do we do from there? So we can figure out how many edges, you know, how many subtrees there are at the root, obviously. We can figure out which nodes are the leaves, because they won't appear in this list. Interesting. Right, because the importance of the lamps is 2 to the I, Really, the order of the subtrees is just the biggest node in that subtree. For instance, the size of the subtree doesn't really matter at all. So, okay, so that means that this edge must be between the root and its largest child. I see. No, not its largest child. The subtree with the biggest number in it. Okay, well that tells us which subtree n is in, I guess. Huh, what a weird problem. Constructive algorithms, indeed. I'm very confused right now. Okay, I'm going to try and work out the example. So we know the root must be 3. And let's see. We know that 6, 1, and 5 are internal nodes of the tree, and therefore 2 and 4 are going to be leaves of the tree. And we know that the first edge must have a 6 somewhere in there, in that subtree. And then the next edge from the 6, I guess it must have a 5 in that subtree. Because there's some edge that goes to a 5. Yeah, okay. So the fact that the next number is 6 means that 6 must actually be the child of 3. Yeah, because otherwise you would just get an edge that contains 6 again. Okay. And furthermore, that's the subtree of 6 must contain 5 because it's the next biggest node. Okay. And let's see. 5 must be the immediate. No. Yeah, well, see, I can't code up this logic, but let me just keep talking through it. So now we see another 3. So 5 must be the immediate child of 6, or else you would have seen another edge sort of containing 5. Right? But we've moved on to another subtree of 3. The subtree must have a 4 in it. That's the next remaining node. Now we see 1. So this is also pointing to 4. Okay, so this is actually starting to be useful because we know that we're basically always looking for the next node, and we're going to the next biggest thing that we haven't seen yet, and we're going to keep sort of drawing down edges. Basically we get the path to the next biggest node. And when we move on to some other subtree, we know that we've actually sort of finished that path. So how do we know that we moved on to another subtree? I'm not sure about yet. Okay, so anyway, we know that this subtree must contain 4 off of 3. And now we get a 1. So it must be that the 1 is the direct child of 3, I think. Whenever we get a new parent, we must have already seen that parent in the tree. And in this case, there's only one edge whose destination we don't know about. And then next we see, and we know that there must be a 4 in this subtree somewhere. And then next we see a 5. And we know that, right, so there's only one more node left, which is 2. And therefore that 4 must have been in the subtree of 1. Well, that subtree is actually just a single node, so now we can reconstruct the graph. Okay, so I think that worked, but I didn't totally use computer-friendly logic there. So one important insight was that we are just following paths down to the next biggest node repeatedly. So the main question is, how do we know when we've hit that next biggest node? Well, it must be when we go back to a node that we've already seen, or if we hit the node itself. Yeah, okay, I think that makes sense. So we're following a path to 6 here, and when we hit the 6, obviously, okay, now we know that we're done, and 6 must be following a path to 5. And now that we've seen a repeat parent, we know that we're done with the 5, and now we're exploring a new path down the tree, and that path must be to 4. Then we see 1, so we're still on the path to 4. And then we see 5, which we have to mark as a repeat. Okay, so when we go back to a new parent, we have to mark in that this the node that we were looking for is the new child, or sorry, is the child of whatever the previous thing was. Right, so we had this path 3, 6, and now this repeat signals the end of that, so it's 3, 6, 5. And now we're on a path to 4, which is 3, 1, 4, and now the 5 is itself a repeat, not to 3, that's the root already, we've seen that, but to 2, and 5, 2, and then that's it. Okay, so that, I think, is an algorithm that we could actually try and implement. Okay, so what do we get? We get n, and then we get this list of which they're calling a, so I'll go with that. We do not want to sort this time. The order is extremely important. So if A is the target, going to be a vector of children. C of So in this case, we're already going back to a previously seen thing. So that means that C of AI minus 1 is the target. I think those are actually just the same case. Otherwise, we're following the path. And those are the only two cases, I think. And we need to keep track of whether or not we're 0 indexing or 1 indexing. Let's just 0 index, I think. So that means we want to print out I plus 1 and C plus 1. Let's make this a vector. So yeah, let's see what we see. This should be not a vector, but a vector of vectors, right? Because each CI is itself a vector. Invalid pointer, huh? Really? Okay, let's just see what we mean by that. Vector deallocator. Index. Okay, so A is supposed to be just minus 1 elements long. What is happening? In the destructor. Six. So confused. The vector LL, pushback LL, that's fine. I'm so confused. n nodes. So n-1 edges. Every node is labeled from 1 to n. So when we zero index, they're labeled 0 to n-1. The root is a0. Target starts at n-1. That might be the problem. Yep. Okay, cool. Gotta get those indexes straight. So there's root 3 is the edge. 3 is the root. It's an edge from 1 to 4, 3 to 6, 3 to 1, and 6 to 5. About 5 to 2. Okay, 1, 4, 3, 6, 3, 1, 5, 2, and 6, 5. That looks better. So the bug there was that the target is supposed to be the next highest not yet placed node. Well, I was just doing the next highest non-root node. So not yet placed, and we're asserting at the end that we sort of got through everything. Okay. Yeah, so hopefully this is right. So just gonna keep following down past the current target. When we hit the target or we hit a node we've already seen, then we know that we reached the current target. So write that down. Write down that we've placed the target and get a new target. And actually just do it that way, right? Yeah, get a new target. And if we get a new node, then that's on the path to the target. So happily, we can always figure out what the previous edge is pointing to. So that's the whole idea. Runtime error on test 1. Really? It's usually this test. Possibly my configuration is a little bit different than theirs. So what part of this is dubious? Let's go back to this association, which I trust. I don't know, it's a little simpler. Target. Same. It's more uniform with the rest of the code. See, n is at least 2. So A0 is fine. I have less than that size. I'm just checking for things that look like they might be sort of questionable. I'm not too sure what would cause this. Similar to 5e submitting. There's a couple things, but nothing that should matter. But you know, the fix here is not going to be to anything that should matter. So have we like not initialized anything? AI is initialized to 0, and we read in. This like super doesn't matter since we're reading it in. U initialized to false, that's actually important. C is initialized to a bunch of empty vectors, also important. Let's see assert. Is there a runtime error on test 1? The runtime error, asserts are also going to fail with a runtime error, so maybe that's not that helpful. Let me just construct a different one. So suppose n equals 2. Yeah. So not equal yi. Okay. Contains n integers, n minus 1 integers. Probably it, actually. So I was sort of descending too far in the target. Yeah, okay. Okay, So this is kind of a neat problem. I had to come up with this constructive algorithm, which I did on, well, mostly on paper. But the point is that because the importance is always dominated by the biggest lamp, we know that we're always just following, right? We have to get down to the biggest sort of unclaimed lamp. So that's what's happening with all of these wires, is that we're always going to the biggest lamp. And then once we get to it, we go to the next biggest. So the only question is, how do we tell when we get to it? And the answer is that we either directly get told that we get to it, or we must start down some new path to some other node. And how do we know that a path is new? A path is new because it starts somewhere that we've been before. So, yeah, it's kind of cool. Okay, well, that was all of the problems. So that's all of this video. Hope it was interesting and you learned something.